before we move into some circuits with inductors and capacitors, we have one other thing we should discuss, and that's how do we treat when we have multiple inductors in series and parallel, or multiple capacitors in series and parallel. Now, I know we talked about capacitors first, but there's a reason I'm going to do inductors in series and parallel first. So the idea here is, just like with resistors, if I have, let's say, just 3 inductors in series, and this is attached to, another circuit. So I don't know what that circuit is per se. I don't really care. But I got 3 inductors here. And I say, well, I might have 3 physical components here, but the circuit is going to see some kind of equivalent inductance, just like we had equivalent resistance. Now, we can go back to the formula, the voltage and current formulas for inductors, that the voltage for an inductor is equal to the inductance times the derivative of the current. And we can go through this and prove the formulas for this. And a lot of textbooks do have that. I'm not going to go ahead and prove it through the textbook the way textbooks do, or just way it's often proved. I'm just going to kind of do it with some intuition here. Let's go back to resistors. Resistors, of course, with voltage is equal to current times resistance. Actually, I'm going to write that slightly different. Resistance times current. And we know that's just Ohm's law. And then we know that resistors in series, they just add. Now, if I look at this voltage and current relationship here, well, I've got a voltage for Ohm's law. I've got a voltage equaling something times another component here, current. Well, with the inductor, it's very close. I've got a voltage is equal to an inductance times, well, it's not my current, but it's the derivative of the current. And if you go back in the videos on how we even showed that resistors in series add, it's going to be the exact same argument here. And so what we wind up getting here is that inductors in series add. And so we get an equivalent inductance of L1 plus L2 plus L3 for this particular circuit. Of course, the general case would be L1 plus L2 plus dot 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 Ln, where Ln is just representing how many inductors we have in series. Now, without too much convincing, you should kind of have a sense of how inductors in parallel are going to behave. Because if inductors essentially behave the same way as resistors do as far as equivalent inductance when they're in series, you can probably take a reasonable guess, and you'd be correct, that when they're in parallel, the equivalent inductance is going to follow the same type of formula that resistors use when they're in parallel. So for this circuit here, you'd have Leq is equal to 1 over L1 plus 1 over L2 plus 1 over L3, reciprocal of that. Or remember, another way that we sometimes write this is that we write that 1 over Leq is just equal to 1 over L1 plus 1 over L2 plus 1 over L3. And just like we had for resistors, if we have 2 inductors in parallel, we can use a shorter formula here. Well, it's not necessarily shorter. It's just one that would be easy to compute in your head. It would be L1 times L2 over L1 plus L2. So when we're talking about equivalent inductance, the formulas we use are the same as the formulas we use for equivalent resistance. So that's the reason I talk about equivalent inductance first, is because it follows how we find equivalent resistance. Now you can probably guess, just based off of what I'm saying here, is that for capacitors that's not the case. Okay, so capacitors in series and parallel. So let's go ahead and just do the same thing we did before. Well, I'll draw 3 capacitors here in series. And then we're looking for some equivalent capacitance. And so if we're looking for some equivalent capacitance, well, let's go back and kind of do the same kind of argument we did before. So we have here that for capacitors, the current is equal to C times the derivative of the voltage. But remember here, what we have for Ohm's law is that voltage is equal to resistance times current. So I don't have this formula at all the same way here. I could rewrite this in some way that would be similar to an Ohm's law. And what do I mean I could rewrite it similarly as an Ohm's law? Well, I could rewrite this as the derivative of the voltage is equal to 1 over C times the current here. So now we also have an issue here that this isn't truly voltage, this is derivative of voltage, but we can see right here we're going to have some kind of different type of relationship here. And when we have a 1 over C, well, I'm now in a case where I could just add up those 1 over C's because it's in the same form as my Ohm's law. But if I added up those 1 over C's, I'd get 1 over, because it's C equivalent, because C is on the bottom, and this would be equal to 1 over C1 plus 1 over C2 plus 1 over C3. Well, wait a minute here. This is not at all like the formulas that we had for resistors and inductors. However, it is similar, because if I think about this for a second, I can rewrite this as C equivalent is equal to 1 over C1 plus 1 over C2 plus 1 over C3 inverse. So what should we take away from this here? Capacitors combine in series like resistors combine in parallel. So that's an important takeaway here, is that these resistors, that these capacitors, when they're in series, actually combine together using a formula that's similar to what resistors do in parallel. And just like we had here, if we have 2 capacitors in series, we get that C equivalent, we could use the shorthand formula of C1 times C2 over C1 plus C2. And then we have one other case we have to talk about, and of course that's when these capacitors are in parallel. So let me just draw a simple circuit here with 3 capacitors in parallel. Now you'll actually see this in circuits quite often, where you'll see these are sometimes called capacitor banks. And sometimes you'll even see them connected just straight up to like VDD and then ground. You'll see them connected up that way. And we already had talked about it in a previous video on one of the reasons why we do that is so that for integrated circuit chips we can get energy right next to the chip because the capacitor is going to store it. But these capacitor banks are also used to filter noise out of power signals, so you can have, again, what's called clean power. So these are very common things to see in circuit diagrams. And if they're in parallel, well, you can probably guess what's going to happen here. If the capacitors in series behave like resistors in parallel, then capacitors in parallel combine like resistors in series. And so what we'd have here is, of course, that my equivalent capacitance here is simply C1 plus C2 plus C3. So it's easy to get these mixed up or flipped or whatever, but it's important to remember that capacitors combine in parallel by just simply adding the capacitances up. And this is actually a useful trick to use sometimes. And what do I mean by useful trick here is there was a circuit that another professor and I were working on for a summer camp project. We have an engineering summer camp, and the circuit, we had a chip over here. It was actually a voltage regulator switching power supply, and on the input the circuit diagram said, well, we need a 45 microfarad capacitor. And at the time we couldn't find one. I mean, you can find 47 microfarad capacitors, you can find you know, other value capacitors instead, but the circuit diagram's like, oh, well, we need 45 microfarads. And so we came up with, well, I want to get as close to 45 as possible. And now, yeah, of course, capacitors have tolerances. Honestly, if we had thrown a 47 in there, it was probably going to be fine. But what we did instead is we put two 22 microfarad capacitors in parallel. Because if we put these in parallel, that capacitance adds up to 44 microfarads, which is pretty close to 45. And we just made sure that when we designed the circuit board that these were mounted close together. Essentially, they were mounted side by side. Because if you're going to do something like that, you want to make sure that they're mounted side by side. You don't want to have one, like, you know, if you're thinking about a circuit board, you don't want to have one here and then one over here, because the whole point is you're trying to combine them together to make an equivalent capacitance. All right, but we're going to stop this video here for today, and we're going to look at a couple quick examples in the next video on how to do these.